Hi, welcome back to this video series on cryptography. Today I'm going to talk about an interesting problem that can be solved with crypto. Okay, let's get into the game. The game is Can You Help Mark? Is title. Mark is a manager and he has two employees working for him, Alice and Bob. Mark's goal is to figure out whether his employees answer differently to this question. Do you enjoy working from home? Meaning Alice answers yes, Bob answers no, or vice versa. So he wants to know whether there is any disagreement. That's basically Mark's goal. There are some constraints. Mark should not know the opinion or answers given by Alice and Bob, the raw answers, due to compliance rules. Alice and Bob can also not share their answers with each other. So that's another important constraint, right? Due to compliance rules, Alice and Bob cannot share the answers. Mark should not know the answers provided by Alice and Bob. And Mark cannot also send out any messages other than asking this question, okay? All right, however, Mark is allowed to read the incoming messages from Alice or Bob, of course. In order to solve this problem, you're allowed to make some assumptions. For example, Alice and Bob can create a private channel, okay, that can neither be sniffed nor be tampered by Mark. So Mark cannot get in their communication channel, essentially. All other channels can be sniffed but not tampered. So nobody can edit the traffic, or nobody's allowed to edit the traffic, but they can sniff the traffic. Okay, and no third parties can be employed. All the channels are only among Alice, Bob, and Mark only, right? All their public keys are publicly available, okay? And of course, the algorithm should be efficient, implementable in polynomial time at most, but should take exponential time to break it, or unbreakable in terms of information theoretic security. Okay, all right, so what is the hint we have? Cryptography may have answer to this question or this game. How do we approach it? So let me draw the picture. Okay, there may be multiple solutions, but I'm going to use a Goldwasser-Mickley encryption scheme that we talked about, and I will apply the idea of homomorphic encryption to solve this game. Here is manager Mark, right? Mark has two employees reporting to him, Alice and Bob. So what is he going to do? He's going to employ public key cryptography idea, but remember, Mark should not know the answers given by Alice nor Bob. And Alice and Bob cannot exchange their answers directly to each other, okay? So how do we solve this puzzle? It turned out that there is a neat idea we can employ. If we use Goldwasser-Mickley encryption scheme, we can solve this problem. So the manager M generates a key pair, right? He generates a public key and private key pair. He keeps the private key, of course, to himself and publishes the public key made of two numbers, N and Z. N is a public key and Z is also a public key, but N is made of two numbers, P and Q, and he keeps P and Q private, okay? So N is equal to P times Q. P and Q are composite, P and Q are prime numbers. He multiplies them to obtain a composite number, okay? You can assume P and Q are distinct prime numbers, odd prime numbers, okay? All right. So this is basically the setup. What is the Z then? Z itself is an element from the set of non-quadratic numbers, okay? Non-quadratic residue numbers, okay? What it means is that it doesn't belong to a quadratic residue set, which we talked a lot in previous segments, right? Essentially, Z satisfies this interesting property that this is quadratic residue, by the way, that if you compute the Jacobi symbol or the Legendre symbol, say, let me use Jacobi, you can substitute by Legendre as well because we're going to use P and Q now. If you plug in Z comma P to Jacobi symbol function, we should get -1, right? And the same for Z with Q, okay? We talked about Jacobi symbol in my other video, so you have to watch those or read about it elsewhere. Okay, so this is the constraint. This constraint will make it difficult to break this crypto system, okay? All right, so what is the deal now? The deal is that he will publish the public key. This is public key, just to be clear, to the world, or everybody knows about it, assume like that. Okay, so what will Alice do? Alice will pick his decision, right? He wants to answer a question, do you enjoy working from home? So his decision can be either 0 or 1. 0 means no, 1 means yes. So let's call it Alice's decision number M underscore A. Okay, the message that Alice will send. It can be 0 or 1. Same with Bob, M underscore B, 0 or 1. Okay. But he cannot, they both can't share M underscore A or B in plain text. So what they are going to do is they're going to encrypt the decision message, right? M underscore A, using Goldwasser-Mickley scheme, right? And send this, so like this. They're going to use the encryption scheme made of Goldwasser encryption scheme, Mickley encryption scheme. Bob will also do encryption of the message. But you may be tempted to think that you will just forward the encryption output to Mark. But that'll be wrong, because Mark will then know who answered what. So that now there comes the trick. Okay, M underscore B. Alice will send this number to Bob. Bob will take this and multiply it with his encryption, right, of the message. He already did it here, and he's just going to multiply whatever Alice has sent. Okay, so he's multiplying two ciphertexts, and now he's going to send, let me call this as a ciphertext C. Okay, he's going to just send C to Mark, the manager. What Mark is going to do, he's going to decrypt C. So Mark will now do decryption, because he has the private key P and Q. So he will decrypt. The decryption process will be simple for him, because we talked about the Goldwasser-Mickley algorithm. So the decryption process will basically take the ciphertext and applies P comma Q. Okay. So what will Mark learn? Actually, we talked about homomorphic encryption earlier. In this case, the homomorphic property of the Goldwasser encryption scheme is that when you multiply two ciphertexts and try to decrypt that, you will get the actual sum of the plain text. So what will Mark get is basically M underscore A plus M underscore B. Okay. By the way, the plus is done in a special group, right? Remember, the messages belong to either 0 or 1, right? Messages can be either 0 or 1. So what if both of them have selected 1? The answer will be 2, right? Which is outside this the set. So we do mod 2. Okay, this is basically mod 2. When you add messages, you have to do mod 2. Otherwise, you're going out. But it's not exactly addition. You could also imagine like an XOR. Okay. So all Bob does is multiplies his ciphertext with Alice's ciphertext and send it to Mark. Mark basically computes the decryption of the incoming ciphertext, and he figures out essentially XOR of, is nothing but XOR, which is same as plus in mod 2, right? 1 plus 1 is 0, because 1 plus 1 is 2, and 2 mod 2 is 0. Okay, so essentially Mark figured out the answer, which is basically whether his employees agree or disagree. Okay, that's all. So now I will show you the demo. I wrote a little Python, and I will now show you the demo for that. Okay. So the demo is going to be showing you the idea of this game. Okay, so let me walk through I will skip the Jacobi symbol definition and things like that, because we talked about a lot those things. So what is more important for us is to use the main function and just walk through the steps, right? Why don't I just run it and then we'll see it. Mark is broadcasting his public key, N and Z. Alice encrypts her decision using Mark's public key. Alice sends her ciphertext to Bob, that's this part. And then similarly, Bob encrypts his decision. Bob multiplies his ciphertext. Bob sends the resulting ciphertext to Mark. And Mark decides by decrypting and then concludes whether both have the same answer or not. In this case, they both have the same answer because I said it so. Alice encrypts her decision to be 1, which means she likes working from home. Okay, in this case, they're actually disagreeing, right? Because Alice said 1, Bob said 0. That means they disagree. And I wanted to make sure that you get the idea of homomorphic correct. Alice is encrypting her message using Mark's public key NNC, right? And then she sends to Bob. Bob does the same. He encrypts his decision, which he says he doesn't like to work from home, and multiplies it with, you see here, this is where the multiplication happens. He multiplies his ciphertext with Alice's ciphertext. Of course, we work in Z star n, so the answer should be within n. That's the reason why we are doing mod n here, right? And now he sends that to the manager Mark, the ciphertext C, which is the multiplication of those two ciphertexts. All Mark does is he's decrypting, right, using the private keys that he owns. And if the answer turned out to be 0, that means they both agree, otherwise 0 won't come, right? Remember, you're adding two numbers and you're doing mod 2. Essentially, that's what's happening in this crypto system. If they both have 1 and 1, when you add, you get 0 because of mod 2. Okay. If they disagree, then they will have answer to be different. Okay. So let me try that. Let's show you now agreement, right? They agree or not. Let's see. Yep. Alice and Bob agreed. As you can see, I took 1 here and then I took 1 here, so they agreed. But the important fact is that the manager Mark doesn't know their answers. You see here, I'm only sending the ciphertext to the manager. Okay, that's all because of the homomorphic property that we talked about. So we can try one more combination, right? What if both of them said, no, I don't like work from home? Let's try that. Yeah, they agree. So why is this happening? Very briefly, I will sketch the math behind it, right? You must watch the other videos to get it to the precision, but very briefly, I will summarize it. So what's happening in this crypto system is that when Alice encrypts her message, m_a, she's basically taking the Z from the public key, right? This is public key, and she writes to her decision m_a, which can be 0 or 1, we don't know, of course, m_a, okay? And she does generate another random number x, which we didn't talk about, but we talked about in other videos. And she writes it to power 2 mod n. Okay, this is her ciphertext. What about Bob's ciphertext? Bob would have something like the same structure. He will be doing m, okay, one moment, m_p. It's not m-p, this is m_p times some other random number y, which is also kept private. He generates that, right? Okay, mod n. Okay, so what happens when you multiply these two numbers? Essentially, these two numbers are multiplied here, right? This is the reason why I said multiplication. When you multiply these two numbers, you will have z. You can now add the powers, right? Because of exponent rules. So m_a plus m_b. Okay. So now what happens to the x? When you multiply these two ciphertexts, you can add the exponents. What about the x and y will be rewritten like this, xy power 2. Okay, we can rewrite like this way. Okay, so what is this structure in mod n again? This is also in mod n. So this means that we are basically sending, or Bob is sending the encryption of m_a plus m_b to whom? To Mark. Okay. So that's basically it, and then we do it in mod n, right? And this part is already taken care because we add these two, and of course we do a mod 2 here as well, right? We don't have to explicitly do a mod 2, but it's taken care automatically in this setup. But you got the idea of when you multiply ciphertext, you can add the exponent, and then you're sending the exponent back to the manager, and he does the decryption. He figures out the addition value, which is same as XOR, because we basically have the message space made of zeros and ones, right? That's the reason why the manager got the answer. If they disagree or not, he's able to find out the answer. Okay, that's basically it. Thank you very much for your attention.